each other, and that's the whole goal of this type of schools. We have a full day of the complete sleep spectrum session, and this morning is more about the observational side of things. We'll start with Aitaro Kato, and
okay.
The floor is yours.
Thank you for a nice introduction, bro. And I deeply appreciate to the organizers, including Anthony and Pablo and the other people who have held such a great school. So I'm Aitaro Kato from ERI. So I'm talking about the long-lasting seismic swarm and the subsequent nucleation of the magnitude 7.6 large earthquakes in Japan. So that's subtitled "The Role of Fluid-Driven Slow Slip." So this is the outline of my talk. So first, one is the water slow earthquakes. So in terms of the wide spectrum of the fault slip. And second, I would focus on the Noto earthquake storm sequence based on the introduction part of about what is the slow earthquakes. So in Japan, we have several kinds of tools to measure the slow earthquakes. So there are just two examples. The left figure showing the map of the nationwide seismic networks on land. And we have also listened to the offshore ocean cable systems for seismic monitoring. And in this year, the NNet is now under construction, and soon we can get new data from this area. And the right map showing the geodetic networks in Japan. So we have many stations on land, but we recently also increased the number of offshore geodetic sensors just above the top of the megathrust subduction zone. So using we have different other tools to measure some slow earthquakes. And based on the accumulation of the observed data, we know that what is the earthquake. So slow earthquakes, now based on the current knowledge, that transient release of the elastic energy through the shear slip at a much slower flow rate than the regular earthquakes of the same magnitude. Okay, if you compare the slip speed of earthquakes in slow and regular fast earthquakes at the same magnitude scale, the slow slip is showing the very slow motion along the fault. So this is a cartoon showing the depth distribution of the slow earthquakes and regular earthquakes in Nankai Trough. So this is a subduction of the oceanic plate of the Philippine Sea plate. And you can see that this red zone is a megathrust earthquake rupture zone. So during the interscience period, this portion was fully locked, so locked by the friction force. But we have the slow earthquake at the downlip extension of this locked zone, and also shallow updip region of the megathrust region. So we know that there are several kinds of slow earthquakes. So I've introduced some of them. So first of they are seismically detected ones. So for example, the low frequency earthquakes. So this is the waveform. You can see the waveform arriving here. So the duration is about 5 seconds. And tremor is now considered to be the swarm of low frequency earthquakes. So the low frequency earthquakes occurred very short time and a very localized region in a very short time. So their waveforms are overlapping. So it's causes such kind of tremors signals. So the duration is the typical duration is about 200 or 500 seconds. And we know that VLFE, so that's a very low frequency earthquake. So predominant period of this event is about 200 seconds. And if you see the geodetic data, we also detect slow slip events. So first time the duration is a little bit shorter. So in this time series of tilt meters, you can see the change of the tilt signals during the, this is the tremor count each by day. The duration is about 1 week, over 10 days scale. And if you see the GNSS stations on land, then we can detect long-term slow slip event. The duration is about 1 year or several years. It depends on each event. Okay, so these slow earthquake occurred so at the downlip side and also updip side in Nankai Trough. And so that is the intermediate type of the flow slip. That is the transitional between the locked segment and stable, more deeper region. So these earthquakes occurs at the transitional zone between two end member deformation. Okay. So I show you the animation to explain what is the earthquake. So it's a good animation created by the IRIS, and it doesn't work. Sorry, it works. So the subduction of the plate interface. So at shallow region, the fault is fully coupled, so locked region as a Nankai trough. And if you go to a little bit deeper, so this is the transition zone where the earthquake is taking place. And at the deeper more region, the stable sliding occurs. So this is the distance on the surface to 3 positions from the shallow and intermediate and the more inland region. So during associated subduction of the plate, you can see the deformation started. So at the slow slip region, you can see the slip is go back, so strain is accumulated. Then the partial strain was released by the slow slip event. So on the other hand, at the shallow depths, this region is just shown as fully locked region, so the strain accumulation is continued. And in other words, if you go to more deeper region, there's no locking, so we don't see any surface deformation associated with stable sliding. Okay, so you can see the lateral change of the strain accumulation in the overlying plate as shown by this rectangular box. Okay. So based on the accumulation of the many observations in the worldwide, we know the earthquakes occurs frequently, especially along the Pacific Rim, as shown by this map. So not only the Japan, we saw the many earthquakes at the many different spots. And in this figure, so everything defined the tremor and the very low frequency earthquakes and slow slip events. So everything, including these earthquakes, has now been observed at several regions, not only Japan, but there are some places we don't see. We can already see the part of the earthquake. So, but I think that we can have a chance to see the more earthquakes if we deploy the more dense seismic network or geodesic networks or more highly good data analysis method to explore the data. And if you go back to the Japan, so that is the earthquake distribution in Japan. So this is the right map showing. So blue shade showing the location of the earthquakes in along the Nankai Trough and the Japan Trench, and red shade indicate the earthquakes, regular earthquakes, especially the large earthquakes in both subduction zone. And so this is a comparison between the slow slip behaviors and the tectonic background between the Nankai Trough and Japan Trench. So this is so if you see the slow slip type. So as I mentioned before, all types of slow earthquake has been already discovered in Nankai Trough. But in the Japan Trench, we have not yet identified the LFE, so low frequency earthquakes. But we have a bunch of the repeating earthquakes in the seismogenic zone. So, but in Nankai Trough, we have not yet observed the repeating earthquakes along Nankai Trough. So there's some contrast between two subduction zone. And of course, the plate is quite different between two subductions. So Nankai Trough is more young and very warm summer structures. In contrast, the Japan Trench has a very old plate subduction and a cold summer regime. And and we can also see the down dip segmentation in the Nankai Trough like here. So you can see that this is a highly locked region and the down dip region. The earthquake zone is almost illuminating the down dip edge of the strong locked region. And also you can see some spots of the shallow earthquake region. On the other hand, the Japan Trench, the most earthquake occurred at the relatively shallow depths and more strong lateral segmentations along the trench. And we can see some down dip segmentation in the off-contour region, but not so clearly compared with the Nankai Trough. Okay, so there's some difference between even along the Japanese islands of the distribution of the slow earthquakes. And of course, regular earthquakes also behavior changes. So and the Nankai troughs, this region is fully locked, but in the Tohoku or around the Japan Trench, we have a magnitude 9.0 in 2011 Tohoku earthquakes, and the other magnitude 7 or 8 earthquakes. And slow earthquakes also occurred within the very close to the seismogenic zone based on the recent observation. And other distinct features of the slow earthquakes are the slow migration. So they show the very slow migrations. For example, the LFE or VLFE and the slow earthquakes. So this is the one example showing the clear migration. So they are showing the diffusional type of the migration. So this is the space and versus time date. So this is the tremor distribution. You can see the tremor migrated to the from here to this direction. And the propagation velocity is gradual. It's very fast at the R stages, but it's gradually decay with the time. And this is the same event analyzed using the tiltmeter. So this is the color contrast shown is a slip amount during this slow slip event. So also slip also followed this tremors migration. So this kind of the speed of at the early stage and the speed gradually decay with the time is kind of the diffusional process. And in this case, slow migration. So slow migration means that 10 kilometers per day. Average migration speed is 10 kilometers per day, but the distance scale is 100 kilometers. And if you go to a more shorter scale, so for example, 10 kilometers, we can see the more small distance migration of the LFE over tremors, then the speed is very fast, so 1,000 kilometers per day. And we know the intermediate migration for the between two phenomena. So if you go to the more smaller scales, then the migration speed is very fast. So it means the diffusion process. And this is a map of the, based on these observations, the scaling law for slow earthquake has been proposed by Satoshi and Berosa, Greg. And so this is the vertical axis, the duration of each slow slip event and or regular earthquakes, and horizontal axis is the seismic moment of each event. So the regular earthquakes follow this trend, as you know, so including the tsunami earthquakes. So the regular earthquakes are concentrated, distributed, very concentrated in this diagram. On the other hand, the slower earthquakes shown in the more spread and more linear trend compared with the regular earthquakes. So duration of slow earthquakes proportional to the seismic moment most of the event. And the seismic moment is defined as the multiplier of the rigidity and displacement of the source areas. And so that they are proportional to the displacement with the squares of the lengths of the faults. And if the D, so slip amount is a constant over the moment, then the seismic moment is proportional to the square of the length. So based on these observations, length is proportional to the square root of T times. So it means it also means the slow earthquake process controlled by the diffusion process. So underlying physics is maybe the diffusion process in the slow earthquakes. And based on this observation, the slow earthquakes seem to be more ubiquitous compared with regular earthquakes. So regular earthquakes are very concentrated in a very narrow zone. On the other hand, slow earthquakes more diverse. And maybe so this region hidden. So we are not access to this region based on the current technique or observation technique. So we must explore this observation window to find the more new slow slip event. So for example, to expand our geoscope, so that is one example. So we deployed a very dense seismic station in the northern coast of the in Japan, southwest Japan. So we deployed 1,000 seismic stations, so as shown by this red squares. And you can see, so we observed the aftershocks following the 2000 magnitude 7.3 Totori earthquakes. And we succeeded to locate the very accurate hypocenters. And so this is one example. So that is please note that this scale is a very, so this earthquake cluster is included in here, and the scale is only 50 meter. Okay, so it's a kind of the scale of the swimming pool. Okay, even though if you see that this kind of very small scale, you can see the clear alignment of the hypocenters shown here. So that is almost parallel to the more larger scale structure. And if you look at this distribution from the down deep, so this is the depth section, so cross-cutting this line, so you can see the most seismicity concentrated within very narrow zone, so less than 10 meter. And this sequence shows interesting behavior. So after the magnitude 2.2 earthquakes here, then the seismicity came up. So this is maybe aftershocks, direct aftershocks. But following some quiescent times, you can see another activation of the seismicity at the down deep part during this sequence. And this sequence shows a very slow migration. So the migration speed is about 30 meters per day. So if this tiny earthquake migration with the duration of days might be driven by slow slip. Even we don't know, of course. I don't know. But this migration can imply some very, very tiny slow earthquakes in the crust. So so I want to say that we need to more expand our geoscope to look for the more tiny and more long durations of slow earthquakes to understand the full spectrum of slow slip slow earthquakes. Okay, and sometimes we can also see some slow earthquakes prior to the mega slow earthquakes. So not so often, but that is one example from the frost shock migrations occurred before the 2011 Tohoku earthquakes. So this is a space-time diagram of the frost shocks. They occurred just above the northern part of the main shock initiation point. And you can see that earthquake migration towards the epicenter or main shock rupture starting point of the magnitude 9.0 earthquakes. So we know we also detect the repeating earthquakes during this sequence, and also we detect some slow movement by the ocean geodetic tools. And so these observations suggest that the two sequence of the migrating frost shocks may be driven by the slow slip transient, and the slow slip transient cause some stress loading onto the future mega slow earthquakes. So as a final kickoff to trigger the magnitude 9.0 earthquakes. Okay, so that is the overview of what is earthquakes, what are slow earthquakes. So they are transitional force slip between the first earthquakes and the stable sliding. So that is transitional behavior, and they are seismically and geodetically detected so far. And there are many interesting features, as I mentioned before. So there are various migrations and come up with before some large earthquakes. And I didn't mention about these three topics due to shortage of time, but the more fluids seem to be concentrated near the source area, hosting the slow earthquakes. And they are very sensitive to the tidal stress changes, and they are triggered by dynamic stress changes. So these two observations are also consistent with a more weak fault along the plate interface by the highly pressurized fluid near the source area. So because the slow earthquakes may be more ubiquitous than the fast earthquakes, so it is exposed to hidden or dark earthquakes occurring in the Earth in near future. So, okay, so that's the end of my first topic. So I move on to the second topic about the Noto earthquake storm sequence in Japan. So this is a picture of the fishing boat after the magnitude 7.6 earthquakes in this January 1st in this year. So this approximates the 4 meter uplift. So you can see that this there are many oysters or winches. They are died, okay, by the uplift. So many, you can say white colors, actually, if you go there. Okay. So I briefly introduced the tectonic settings of Noto region. So this Noto peninsula. So I overplot the seismicity. Okay. So Noto peninsula is here. So the Noto Peninsula is located at the eastern margin, so that is the Japan Sea, so eastern margin of the Japan Sea, and uplifted by long-term cluster deformation. And I overplot the recent seismicity, which occurred within 25 years, so from 2000. And you can see the main earthquake occurs along the Japanese island. And this each dot is the epicenters and color-coded by depths. And yeah, Noto region, you can see the aftershocks following these powerful earthquakes in these years. But if I plot, I plot the big earthquakes in magnitude 6.5, greater than 6.5, but from within the recent 75 years, you can see some concentration of the shallow earthquakes, cluster earthquakes, along the eastern margin of the Japan Sea. So Noto region is also including such kind of broad region where the hosting the more damaging earthquakes in recent years. And actually, the geologic measurements suggest the strain concentration zone is also located along the hills. And also, geological evidence suggests the strain concentration in along the eastern coast of the Japan Sea. Okay. So along the eastern coast of the Japan Sea, so from 25 to 30 MA, here. So as shown by this cartoon, the extensional stress regime was very dominant because of the association with the opening of the Japan Sea. So the Japanese island is extended from the Russian side, so continent. And there are many, so numerous normal faulting were created during this time. And from 3 to 5 MA to the present, the stress field changes completely, so opposite. Now the complete compressive stress regime has been dominant. And this compressed stress regime reactivates the pre-existing normal faults created during the opening of Japan Sea. So that is called the tectonic inversion in the structural geology field. So yeah, I want to say that there are many pre-existing faults along the eastern margin of Japan Sea, and this reactivation is very important to understand the current seismicity. So let's see the decade of seismicity in the Noto region. So from 1985, so this is epicenter distribution in the zoom up to the Noto Peninsula. So you can see this is Noto Peninsula. And in 1993, we have a moment by 6.3 earthquake cluster here, aftershocks. And in 2007, we have also magnitude 6.7 earthquakes here, so aftershock distribution here. And this is years and space along the fourth strike. And aftershock sequence, two aftershock sequence continue, then the Tohoku earthquake occurs. So some seismicity boosts up around here. But very, very few seismicity in the tip of the Noto Peninsula. So that area is called the Suzu area here. So you don't see any seismicity for long times. But from the end of the 2020, the very active seismic storm started here. So it's lasted over 3 years, and then we have a magnitude 7.6 rupture in these years. Okay, so like this one. And so I will briefly introduce some results about Noto earthquake in 2007. Okay, before going to that this year's event. So as a characteristic of this event, the rupture shown in the reverse force slip at the down dip side, but the shallow depth is a more strike slip component is more larger as shallow depth is. And also the aftershock distribution shows a so this is the depth and the perpendicular distance from the fourth strike. So you can see the more highly dipping angle aftershock distributions. So that is also implies the reactivation of the pre-existing normal faults through this 2007 Noto earthquakes. And also, if you look at our structure in this region, so we deployed the dense seismic observation in the on-land region. So this is this result about the stress field beneath the main shock hypocenter. So this is a aftershock distribution, and the background color indicated the P-wave velocity structure embodied by the travel time data using a seismic tomography. And this separation in the distribution of the resistivity structure based on the EM studies. You can find that beneath the main shock hypocenter, you can see the localized low velocity layer and highly conductive zone beneath the main shock hypocenter. So stress field is also very strange, so weird. So the sigma axis, so the largest horizontal stress axis, is more randomly distributed compared with the minimum stress axis. It's a very stable, but sigma 1 is rotated at many directions. So these observations may imply the fluid is coming up, maybe from deeper depths. So they are coming up. So these stress fields, so horizontally isotropic stress fields, and or localized low velocity and highly conductive zone just beneath the main shock hypocenters. And we can also see the spatial temporal change of the aftershocks following the 2007 event. So this is a epicenter distribution of the aftershock right after the 2007 event. The aftershock is very confined with less than 20 kilometers, but the aftershock region is gradually extended to the, especially to the southwestward. Of course, we can see some slight expand to the northeastward, but the most of expansion took place to the southeast direction. So this slow migration of aftershock zone could be explained by some afterstrip coupled with the fluid diffusion. So fluid is coming from the main shock, beneath the main shock hypocenter. So the fluid is, so after the rupture, the fluid is coming, and this fluid may facilitate the afterstrip which propagated along the fault strike. Okay, so let's go to the long-lasting earthquake storm over 3 years. So this is the magnitude versus time. So you can see the storm activity started around the end of 2020. So that is the largest magnitude event in each year, so gradually increases. But they are still occurred at only the northern tip of the Noto Peninsula. Okay, so this earthquake storm activity accompanied the cluster deformation. So this is the time series of GNS stations near the tip of the Noto Peninsulas. You can see some change of the surface deformation shown by these figures. And at very, very early beginning, the horizontal displacement shown in the radial distribution. This distribution can be explained by the shallow dipping tensile cracks. So it's an opening of tensile crack at the depth of about 16 kilometers. And following that, the surface displacement pattern slightly changes. So you can see the more large component to this northwest to the southeast direction. So this from P to B and C, maybe the series of this data can be explained by the series of the slow slip transient at slightly shallow depths, so 15 kilometer depths. So this is schematic figures for period A and period B and C. So the slow slip taking place from the period B and C, and this slow slip causes the stress concentration by the slip up to the upper dip side of the slow slip region. So this stress concentration might cause a long-lasting earthquake storm based on the Nishimura-san studies. So if you look at the seismicities drawing this earthquake storm, so this is a study by the Keisuke Yoshida, so he's also attending this school. And this is a zoom view of the epicenter distribution during the sequence. And so he divided this region into 5 clusters based on the spatial distribution. So this is the depth versus days over 3 years. And so the earthquake cluster started from this southern cluster here and migrated here and migrate to the northern direction. And you can see if you see the depth evolution, you can see the clear hyperbolic or some diffusional type of the earthquake shallowing with the time. Okay, so we can see the persistent upward migration of the earthquakes through this sequence. Okay, so this observation also supports the involvement of fluid from the deeper sources. And not only this kind of the long, so 3 years or several years migration, we can also see some more very short time fluid migration based on the immediate aftershock analysis. So this is aftershock evolutions associated with the magnitude 6.5 earthquakes in 2023. You can see that so this is the depth and this is the direction to the perpendicular to the fourth strike. If you see this panel, so the aftershock shown is expanding to the shallower depths, so the along fourth strikes, but the speed is very fast, so 20 kilometers per hour. Okay, so following this event, we have also magnitude 5.9 event. It's the largest aftershock following magnitude 6.5 earthquakes, actually. And this, after following this earthquake, you can see also the very rapid earthquake aftershock front is migrated very rapid, so 20 kilometers per hour. So this rapid migration can be explained by the fault bubble model, which was proposed by 30 years ago by Rick Simpson. And so beneath the seismogenic zone, some shears is present. Then the fluid is moving up by the buoyancies. And if there is some shear, the fluid pressure is gradually accumulated and gradually increased. And then if the earthquake rupture occurs, then this shear was broken, then the fluid is migrated along the rupture zone. So this rapid fluid migration can be tracked by the immediate aftershock evolution. So I just shown the very simple 1D diffusion equations, and I estimated the permeabilities during this fracture stage. Then the permeability is roughly estimated to the 10 to minus 10 square meter. So it's very, very, very fast values, very large values. So upwelling of cluster fluid along the fractures or permeable fault zone could trigger the rapid migration of immediate aftershocks along the fault zone. So after the rupture, so there are many fractures at the time, so maybe fluid can flow along the permeable fractured fault zone. But soon the sealing started right after, so heating or sealing causes a gradual decay of the permeabilities. Okay, so this is a diagram showing the cluster process during this long-lasting earthquake storm. So we have magnitude 6.5 earthquakes, slow slip taking place here. Maybe this slow slip was driven by the fluid and storm activity occurring at the up dip side of the slow slip region. And right after the magnitude 6.5 event, the fault fluid is maybe migrated to this fractured fault zone, or some upward migration to surrounding the fault region. So in that case, so we know the location of active fault, and this aftershock distribution did not match with this deep extension of active fault. Okay, so persistent upward migration of fluid causing the gradual weakening of the surrounding active faults or unrecognized faults in the storm region. So then we had a magnitude 7.6 event here, so this January 1st, and after expanded over the 100 kilometers. So that it causes severe seismic or tsunami damages. And so, okay. So, sorry. So this is the aftershock distribution following this magnitude 7.6 event. So the main shock hypocenter is located around here. So this is the aftershock distributions, and the color coded by the depth. So you can see the southeast dipping structure dominant in offshores. And if you overplot the traces of the active faults in the oceans, which was proposed by the HARP in Japanese government committees, then the aftershocks roughly followed or matched the source fault or the surface traces of active faults. That's proposed before the magnitude 7.6 event. Okay, and if you look at the cross section of aftershocks from the northeast side, from the southwest side, so at the ocean side, we don't have enough seismic stations, so the depth accuracy is very bad. So the absolute depth is not correct, but relative distribution seems to be okay. And if you see the this profile is the northwestern dipping for structure dominant. Okay. But if you go to the tip of the Noto Peninsula, you can see the southeast dipping plane can be seen. And around the epicenter of the magnitude 7.6 event, you can see the subparallel, maybe 3 or 2 subparallel faults can be recognized. And if you go to the southeastward, then the southwestward southeast dipping fault structure seems to be continued, except for the western edge of the aftershock region. So this region shows the more complex structure, including the conjugate faults or different fault strike distribution. Okay, so and this earthquake occurred, caused a significant uplift of the Noto Peninsula, and also caused a very strong shaking along the Japanese island. And Vincent May, so he will talk about the source process tomorrow. So please ask him to the details of the rupture process of these earthquakes. Okay, so I'll skip there. But I just want to mention about just beginning of this earthquake. So, this Aitaro suggested some slow initial rupture. So this is the result of the back projection during this magnitude 7.6 earthquake. So this is the space versus time. So you can see the very early portion of the rupture stage, the radiation is almost stayed within the earthquake zone region here. Then the 20 seconds later, the rupture bilaterally propagated to this direction, to the northeast direction. And if you look at the waveforms, that was recorded here, so nearby the very nearby the source region, epicenter region. So this is a wave packet of the magnitude 7.6 event here. But you can see the another prior some wave packet. So that is corresponding to magnitude 5.9 event. So that was identified as JMA. And if you see that, so that is 2 minutes earlier, so magnitude 4.6 event, and 2 minutes earlier, we have a magnitude 5.5 event. Okay, and if you zoom up this waveform at the early beginning of the magnitude 5.0 event, so you can see that it's a P wave, and this high frequency coming, and you can see some slight change of the frequency component from here to here. So it's a more long period component is rich compared with the early portion of this waveform. So maybe I think the magnitude 7.6 started around this timing. I didn't mention in the later slide. But if you zoom up furthermore, so we found magnitude 3 class earthquake here. So there's the P wave and the S wave of magnitude 3.5 earthquakes. So this is the epicenter distribution of these immediate flash shocks. So they are concentrated the northeastern side against the epicenter of the magnitude 7.6 event. So I I don't have enough time, but okay, if I just compare the magnitude of 5.9 event in this years and in last years, okay. So this is a low waveforms observed in the FNet station as shown by this map. So these two events occurred close to each other here, and so this is the amplitude of between this first 7 or 6.5 seconds. You can see the amplitude is almost similar and decay with the distance for both events. But if you look at the more long period size, so from the 20 to 50 seconds, then there's some clear difference. So in the last year's magnitude 5.9 event, we see some increase wave packet here, but we don't see any temporal change of the amplitude. But if you look at the magnitude 5.9, so that is the immediate flash shocks before the magnitude 7.6 event, you can see the clear increase of the amplitude about 6 or 7 seconds after the magnitude 5.9 event. So we saw, based on this, that we consider that this is a magnitude 5.9 event as a flash shocks, which can be separated to from the source process of the magnitude 7.6 event. Okay, so if you look at more earlier time, so we also observe some very concentrated intensive flash shock sequence here. So these flash shocks occurred very tiny spot in this map. Okay, so it's continued about 1 hour. Then the magnitude 5.5 event, or other more big event occurred right before the magnitude 7.6 event. Okay, so look at the depth section of these flash shocks. So flash shocks are denoted by blue circles, and the gray dot is distribution. So that is the preceding seismicity before the July 1st in last year, up to the magnitude 7.6 event. So this is the depth, and this is a cross section. This gray dot shown in the two clear planar structure, and this planar structure corresponds to the source fault of the magnitude 6.5 event. So that this magnitude 5.9 event, so that the immediate flash shock occurred almost same location of the pre-existing seismicity. Okay. So, and this some localized flash shocks indicates fluid-driven slow slip during the flash shock stage and facilitate the stress loading on the main shock nucleation point. So this is the aftershock distribution, so you can see the change of the seismicity. So seismicity more on the average is a more shallow and extend to the surface. Okay. Okay, so I will skip there. And sorry, yes, so that is a cartoon showing the summarize my talk. So fluid-driven slow slip causes stress loading onto the surrounding faults. And not only the stress loading, the fluid diffusion into the faults, it also causes the gradual weakening of the surrounding faults. So the stress loading and the weakening of the fault strength, so both process are very important as a preparation to the magnitude 7.6 rupture. And so this is a cartoon, final, and so the flash shock sequence is occurred right before the magnitude 7.6 earthquakes in using the pre-existing structure, which was activated by magnitude 6.5 event in last year. So the combination of the slow slip and the subsequent intensive flash shocks may trigger the magnitude 7.6 rupture. Okay, so that is my summary about Noto earthquake. And so the long-lasting earthquake storm has shown the persistent upward migration over 3 years and resulting in magnitude 7.6 rupture. So the stress loading of the fluid-driven slow slip and the gradual weakening of the faults could play an important role as a preparation stage. And some local flash shocks indicate the involvement of fluid-driven slow slip. It's a very tiny one. But they occur at the pre-existing fault structure, so the reactivation of the weak structure is very important. So combination of the slow slip and subsequent flash shocks may trigger the magnitude 7.6 earthquakes. Okay, so I stop here because I don't have enough. So thank you very much for your attention.
Have you looked at geomorphology and if you have terrace risers above this on the northwestern coast of Japan that correlates with this seismic activity?
Yes, so there's some Koreans, Japanese Koreans, who looked for the terraces associated with these earthquakes, and they identified three change of terraces during the over 6,000 years. But this time has the largest one. So 4 meter is the largest.
How long is this one? How many thousand years?
6,000. 6,000. And but previous 2 steps is more small. So this one is the largest one. So 4 meter is the largest one. And yes, as I show you the map of the active faults traces here. So yeah, so with most of these active faults, active faults seem to be slipped during this event because of the surveys of the how to say that, the temperature change of the reflection image, so before and after the earthquake. So there are some step or some change of the reflection image crossing these fault traces. So that is also consistent with the uplift of the northern coast of the North Peninsula.
There's another question by Nicolas here.
Thanks very much for a super interesting talk. There seems to be a systematic association between diffusion-like process and fluids.
Mm-hmm.
Fluids are not the only things that can diffuse. I mean, slip can diffuse.
Yeah,
right?
yeah.
Is there like, I mean, the permeability you inversed, for instance, 10 minus 10 square meters.
Mm-hmm.
That's extremely large. That's
exactly.
more than you would expect from a pile of gravel outside.
Yeah.
So it's very, very, very large type of permeability. And is there any clue that it could be something else? Like, slip itself can diffuse.
Yeah, I see.
Elastic material. So.
Yeah. It means so slip plus stress is also propagated out of the fault. So yeah, it could be, but I interpret that many studies suggest some fluid involvement during this earthquake swarm activity. So the fluid may exist at the down dip side of the seismogenic zone. So this very high, but if the fractures collected at the larger scale, then the fluid can move very fast. If overlapped, I think, but it's very short lifetime. After that, maybe healing of things should take place soon. So, but a very short time, we can, it could be possible. But of course, it's my hypothesis. So, we should consider it. Yeah.
Thank you, Aitaro. That was a very nice overview. I have a question related to the first part of your talk.
Okay.
The scaling.
Yeah.
So if you draw a line from LFEs to slow slip events, I agree that you find that the moment scale is the duration of those slow slip events.
Yeah.
But I don't think you can call that a scaling law.
Mm-hmm.
I don't think it's a scaling law because a giant SSE, well, a long duration SSE is not a giant version of a LFE. We're connecting different phenomena. So it seems to me that this limit is more a detection limit.
Okay, yeah.
And so I'd like to hear your take on that. But I think it's misleading to call that a scaling
Okay,
law.
sure. Okay.
And the other thing is about the diffusion, the idea that that we would see diffusion during slow-slip event. If you look at the propagation of the rupture front during a slow-slip event, from tracking the tremors directly from geodesy, you don't find that the length scales with the square of time. It's more proportional to time. So
it's sometimes. But we can see.
I don't think you generally see a diffusive process during the propagation
I see.
of the slow events.
In the maybe in Japan we can at the second point we can see the frequencies are such kind of the diffusion pattern of the tremors especially tremors. We can frequently see such kind of the diffusion pattern. So, but of course, sometimes we can see the linear migration. So yeah, I don't know which is correct, but yeah, not only very few. Yeah, there are several cases, many cases. We can see such kind of the diffusion pattern of the tumor migration.
Okay. For one last question by Alex.
Just a quick one. So we've been interested in the relationship of earthquake complexity and tsunami generation. So I was wondering, specifically in the northeast or for the faults offshore, what could you say? What is seismicity telling you about faults offshore and potential more slip offshore than?
Yeah, a good point. Yeah, thank you very much for this topic. And yes, if you look at the aftershock distribution, I know it takes time, but there are many fault structure. It's connected to the surface in offshore. So, and deep angle is gradually steeper to the surface compared to more deeper depth is more gentle tipping. So, I think the more steep fault plane can be seen, so that this steep angle can generate tsunami near on the surface. Thank you.
All right.
Thank you very much for your attention. Thank you very much. It's okay.
Sleep.
Seems cool. Your neck. Okay, like that.
Yes.
Yeah, I'm not quite sure it will work. Yeah, I will not use it. Just the pointer.
Just
yeah.
Thank you, Aitaro. Our next talk is by Bryan Raimbault.
It's the light. This one. Yep. So thank you. My name is Bryan, and I would like first to thank the organizer for giving me the opportunity to present my work that I've been doing during my PhD with Romain Jolivet and Eric Calais mostly. And today I will present you some really interesting behavior that we see in the wake of the large earthquake in Haiti. And especially that we saw some faults that are shallow and weak and diffusing the stress that is imparted to large earthquakes. So first, back to basics, you all know that. But in the core seismic period, we have the rupture of an earthquake due to the interseismic strain accommodation on the interface. And after that, in the wake of the earthquake, a lot of post-seismic mechanisms are occurring. A lot of them, such as aftersleep, aftershocks, viscous relaxation, triggered earthquakes. And actually, we are accommodating the stress changes in the crust due to an earthquake. And this is really interesting for us, geoscientists, because it allows us to probe the rheology of the crust. And in the following, we'll be mostly interested by triggered slip on nearby faults. So if we speak about triggered slip on nearby faults, you have this study from Xu and collaborator after the Ridgecrest earthquake, where they identified a lot of lineaments and surface discontinuities into the phase gradient images, and they see some faults that are moving in the direction of the prevailing tectonic stress, and some other faults that are moving in the opposite direction of the prevailing tectonic stress. So they call that prograde when it's in the direction, and retrograde when it is not in the direction. So, for example, in Ridgecrest, the red one are prograde, and the blue one are retrograde. Blue is, in that case, means it's left lateral, and red, right lateral. So they found an explanation to this kind of behavior, and especially with an elastic response of the crust to the core seismic stress changes. And what they say, for example, in the case of the retrograde deformation, is that the fault zone where the slip is occurring is actually in an area of compliance, which means that the shear modulus in this area is reduced compared to the surrounding, so that any stress that comes by can modify what has been accommodated on the fault. So that actually, if the stress is negative and coming to the fault, it reduces what's been accommodated, making an apparent fault slip that is opposite to the prevailing tectonic stress. And in the other case, it's more classical frictional slip, where it overcomes what's on the fault and makes it slip. So, as you saw in my title, we are interested in Haiti, and especially after the large earthquake occurring on the southern peninsula of Haiti. And do we see such kind of events after the large earthquake that occurred there? So we are on the southern peninsula of Haiti. Two large earthquakes occurred there, the 2010 earthquake in this area, and 100 kilometers to the west, the 2021 earthquake. And the largest part of this talk will be dedicated to this black square, where the 2021 earthquake happened. And the rupture of this earthquake was a bit odd because it ruptured the thrust that had a direction towards north, and then propagates onto a left lateral fault towards west. And it did not involve the main left lateral strike slip fault, which is the EPGF. So, one study looked at the post-seismic period of the Haiti earthquake and used ALOS 2 phase gradient stacking to identify some fractures in this area. And so this is a study of Yin and collaborators. And so they identified some structures that moved in a left lateral way and some others that moved in a right lateral way. So some are prograde and some are retrograde. But the study didn't look at the time dependency of the behavior of this apparent slip. So in the following, we'll use Sentinel-1 data to see if all these faults are actually slipping in the post-seismic period. And spoiler, they are. So we use all the Sentinel-1 images after the 2021 earthquake, and you have there the result of this analysis with the cumulative displacement map in April 2022, so we use all the days, and what you see is that we have some structures that are delineated by the black arrows. So we have the time series, we can do some profiles and look at the slip evolution as a function of time. This is what is done there for the profile AB, and you can see that we have a slip evolution as a function of time. You have your fault here. And this slip evolution as a function of time presents logarithmic decay. So it's mostly characteristic of after slip, but here it did not happen on the fault that ruptured, which is a bit weird. So we did this kind of analysis, extracting the fault offset as a function of time for all the faults that we identified, and we have a lot of them. And what you can see from that is that we have two families. Of course, the red ones that move in a left lateral way according to the left lateral transpersive tectonic context, and the blue ones that move in a right lateral way against the, opposite to the prevailing stress in this area. And it's quite interesting to see that if we do a profile into the last acquisition of our time series, you can see all these faults. But you can also see some other features that we decided not to take into account because they were too small and inside the INSAR uncertainty. So we have 14 fault segments holding left lateral and right lateral motion. And so that actually some behave according to the tectonic contracts and some others do not. But they all present a logarithmic slip decay as a function of time. Now, if we look at the Coulomb stress, and especially the shear stress changes after the earthquake, so due to the rupture, this is what we have. so we impose here the direction, so not all the faults might fit in the good area, but believe me when I say that, all the faults that are moving in a right lateral way are in areas where the shear stress is negative, and all the faults that, 2 minutes, okay, and all the others are in area where the shear stress is positive. So is it a compliant fault zone? Actually, it might not be the case because we have a characteristic time for slip, and the slip evolution is a function of time. Maybe a viscous response, but this means that the fault viscosity, I would say, and that actually the drop of viscosity for a fault that would move for 5 to 10 weeks will be very high in terms of drop of viscosity compared to the surrounding. So we think that it is most likely frictional. And if it's frictional, we can use those kind of equations that relate the fault evolution as a function of time and to extract some parameters such as A minus B. And we assume here that it is rate strengthening in the sense that the faults see the stress and they are diffusing it and we obtain value that are close, for all of them, close to 10 over minus 2. So yeah, you have on the top the left lateral fault and on the bottom a right lateral one. So if we sum up now a bit, and yeah, you can only look at this graph because it's the most interesting one. You can see that we have this separation between the left lateral fault and the right lateral faults, as we saw already in the figure, that are actually presenting that we have an increase in shear stress for, positive shear stress for left lateral fault and a negative shear stress for right lateral fault. And so that actually we think that the faulting type depends on the shear stress variation that is applied on the faults. And it only takes small values of shear stress to trigger slip on them. So that fault should be at a very low absolute stress level before the earthquake. And then they are very shallow because we look at some profile and see that the fault zone width is only on a small area. So we have secondary faults that are weak, passive markers of past earthquake diffusing activity, diffusing stress. And this is not the only example. We looked a bit after where a sequence of magnitude 5 earthquake happened, and we have 2 faults that were activated by this sequence. So you can see that there is an increase of slip on these faults right after the event. And they are located in an area where the column stress has increased. Actually, we looked also after the 2010 earthquake, so 10 years before. We only had the ALOS-1 data at that time, but still it's enough to see that we have some faults that were slipping, although we only have one line of sight, one looking direction, so that it's hard to tell about the fault motion, but if it has been more horizontal, we will see such kind of pattern. So, as conclusion, we have multiple secondary faults activated after large earthquake in the area. We have frictional rate strengthening behavior for all the segments, and a strong link between co-seismic stress redistribution with faulting type. And so that we think we have secondary faults that are weak passive marker responding to stress variation. So what's the role of this secondary weak shadow faults? Actually, I like to use this picture of Segal from his book in 2010, because if the quantitative behavior of this fault is actually to slip when stress is coming by, during the interseismic period, they should somehow release the stress buildup on the area, and it has some kind of implication about the shallow slip deficit, because if you take this figure and you see the shear stressing rate for a vertical strike slip fault, this is the black line you should obtain. And if we have faults that are slipping while stress is applied on them, we should obtain the red one, so that actually it's less than we were expecting. So yeah, it has important I don't remember the word, but it's important for seismic hazard assessment. Yeah.
For questions, Roland?
That was a great method. Can you tell, is the data good enough that you can tell how deep the response extends?
Yeah, for most of them, it's possible. The best way would be to model and see what's the depth, but didn't have the time yet to do that. But mostly they have the same depth, and which is very shallow. I mean, it doesn't go deeper than 2 kilometers, which is where I compute also the stress changes.
Thanks for that. Do you see any motion in the co-seismic interference on this one?
On some of them, yes, but not all of them. So yeah, one of the big questions was, is it some kind of post-seismic of this fault because they were sleeping during the co-seismic period? If it had been the case, actually they should not sleep all the same way, but yeah, it is the case, so.
Great talk. So I know you have an excellent co-seismic slip model, but there is still some discussion about the geometries of this fault system and
Definitely.
dynamics of the co-seismic event. So is any of this maybe also a marker for what exactly happened during the earthquake? Because it should be, right? I mean, you just look versus the Coulomb stress model, but there's also dynamic stresses which are very large, much larger than the static.
Yeah. Yeah, it's possibility that some kind of dynamic triggering on these faults could have make them sleep, but yeah.
When you compared to the Coulomb stress analysis, did you see any oddballs? Was there anything not quite matching up with the static slip Coulomb stress that you inferred from your slip model?
Yeah, actually, yeah, there are some kind of variations, but the slip model is like a static one, so it's with a layered medium, but it's not perfect. I mean, it's like a state of view at some point. So yeah, there might be some kind of differences. So, but we can talk about it. I know that you're working with Zoe on that, and I would be happy to.
Last question by Chris.
Yeah.
Very last talk, thank you very much. So you have this observation that small changes in stress and Coulomb stress cause slip, and then you talked about the idea that this might mean that the fault is quite weak. But another possibility is that the stress is quite close to some threshold, so the ratio of stress to failure stress, if you want, is quite high. Can you distinguish between that or say a little bit more?
Definitely it will be tough to distinguish between both hypotheses, but yeah, the fact that actually we don't know how these faults should sleep at the beginning. So this is one important point. So are they actually in a failure, almost failure state? I cannot tell you because I don't know how they are sleeping. So that actually, if it wasn't the case, we wouldn't see the fault moving. If all the faults were moving in a left lateral way according to the transperceptive tectonic context, and that they were close to failure, we would not see them moving the other way. That's my point, because we will go back then to the hypothesis that Xu and collaborator did after the Ridgecrest earthquake.
Thank you. We're going to move to the next talk. Thank you, Ryan. Last talk before the coffee break will be given by Colin Pennington on quantifying the complex rupture characteristics of microearthquakes.
Yep, and that's in the pocket.
All right. All right, so I'm going to be talking about complex ruptures of microearthquakes. So, first of all, let's define what a microearthquake is. Here, I mean anything that's less than a magnitude 3. To give an example of what that means in size-wise, this is a magnitude 4 slip inversion right here. It extends maybe 2 kilometers horizontally and a few more kilometers down in depth. This is a magnitude 2. So it's basically that size there. It has a rupture length of 50 meters. To the left, to the right, and then down maybe 100 meters. So these are very small earthquakes. But why do we care about microearthquake ruptures? Well, they occur more frequently than large magnitudes. They will occur on faults that may never host a large magnitude earthquake, so they can tell us information about those faults. And they provide estimates right before a big earthquake happens, like foreshock behavior, and then events that happen right after a large earthquake. So we can study how big earthquakes affect ruptures of smaller earthquakes and fault properties. And we can also use them to inform us about how fault properties are changing along a fault system. But for the longest time, we've always treated these microearthquakes as very simple earthquakes because it's easy. We just assume they're a circular rupture, and we apply that model to them, and then we can estimate their durations for a bunch of earthquakes, get stress drop, all these different parameters, and study broad regions very easily. And the reason we could do this and make this assumption is for a number of reasons, but we assume this because it's easy. We can apply it to many events. The trade-off for this is we lose a lot of information, and maybe the model does not actually really apply to these events. And so the reason why we apply to these small earthquakes is because we traditionally were very far away from them. So, for example, if you're very far away from two cars here, you might, and I ask you what type of cars these are, you might not be able to tell me that much information because you're very far away from them. So you might just be able to say big, small, which you can apply to earthquakes too. It's a big earthquake, it's a small earthquake, and then maybe something else about like red or green, like high or low stress drop. But nowadays when we have networks that are deployed much closer to the earthquakes, we can get a lot more information from them. So now if you're closer to these cars, you can say, and I ask you the question, what type of cars are these? You can tell me it's a truck and a compact car, and it's a Ford or a Fiat even. So that's what we're doing now. We have networks that are deployed much closer to these earthquakes so we can look at them more precisely. And so now we can do this with a number of ways. First being finite fault inversions, where you invert the slip on the fault surface. This is time consuming, and it might not work out when you apply it to earthquakes, so it's a big trade-off. Other ones are source time functions, where you look at the moment rate through time for an earthquake, so you can see multiple bumps and complexity there. Or you can just look at the spectra of an earthquake and see if it deviates from our assumed simple model. And so again, this one's hard, takes a lot of data. You might apply it to an event and it might not work out and may never converge. These two are easier and the ones we're going to be talking about because it's easier to converge to solutions here. The problem is all these rely on using an empirical Green's function, which is a small event next to the big event that we divide out the path and side effects from. And we assume that small event is small enough that it won't affect the source of the target event that we're interested in. So again here, like the small event, like will not affect the big event because it's so small, it won't affect its spectra. Or in the source time function, it's small enough that if you divide it out, its small little impulsive delta function will not affect the big earthquake's source time function at all. The problem is they're difficult to get because there's a lot of parameters. They have to be small, at least one magnitude, in order to have this preserved area of the large event spectra that you're interested in. Or the source time function here has to be small because we can stretch it to make it fit the bigger source time function of the target event. But if the source time functions like this, you can morph it in and out. But if the EGF is not small, you can only get something that's equally sized to it. So this is the problem with these events. And then again, it has to be close. So 2 to 4 rupture lengths with for microearthquakes that's like 200 meters away. And then it has to be similar to the target event's rupture, which is very difficult for small earthquakes because you might only have a few measurements to define its rupture. But the area we're going to apply this to is Parkfield because we have the borehole network right there. And so we're going to be using source time functions and source spectra to estimate complexity for earthquakes. And so here's the spectra. So basically, we do the spectra ratios for a bunch of events. And the way we define it as complex or not is to basically compare it to our omega square model, which assumes that it's simple. And so the idea is if it deviates from this model, then it's not simple. And so basically, we measure the ratio of its deviation. So we're deviating, this is the spectra ratio, and this is our fit model is the dashed gray line. And so then we measure its deviation right here. So you can see this one deviates a lot, the red line there. This one deviates some. These don't deviate at all because they're basically flat red lines. And we measure the peak deviation from these 2 points, the peak and trough. And then that gives us our estimate of complexity. If it's for this region, if it's over 1.8, it's fairly complex then. And so these two are complex because they deviate a lot, while these ones too do not. They're simple events. Now for source time functions, it's a little easier because you can see right here, this is our target event, this is the EGF event, which we have multiplied by 9 to make it similar amplitude. So all we do is convolve the Gaussian pulse with the EGF to see if we can get the target event, and keep adding pulses to see if we get there. And so you can already see the target event's complex because it's different. It has 2 bumps instead of the 1 of the EGF. So we know this should be a complex event. And so this is our first Gaussian pulse we add here, and you can see the result is this predicted right here, and this is the residual waveform left over, so we have more to get rid of. So we add another pulse, we're getting closer, we look at another one, we're getting closer, then we add this one, and it doesn't improve that much, so we stop here and don't add that one in. So this is the general process of it, and you basically look at the residual between your observed and your synthetic waveform. And so the one issue here is, again, we have a noise level for all these observations, which is around 50 hertz. And so the pulse for like the EGF event here is about appropriate size. It's above our noise level. This is our minimum basically pulse size. So for these big events, we can get out all the source time function from it. But when we go further down, like down to 2, we're dropping below that noise level. So we might be able to get some of the complexity out of it, but not the full source time function for the event. And then if we go down to 1.4, we're well below, so we might just get 1 pulse there. So again, we have a resolution limit to all of this, which you have to keep in mind for these measurements, which come into play later. But again, basically down to 2, we're okay. We can get out some complexity for these events. And so here are 2 examples for simple events. So again, we have our spectra here that doesn't deviate that much from the assumed model. And here are our source time functions, all single pulses. And you can see there's some directivity here down to the southeast direction of the San Andreas Fault because they're becoming narrower as down that direction. And then again, this other one, again, also has a southeast rupture direction, also single pulses here. And again, simple spectra. So they both match, which is a good observation. We want these 2 observations to agree with one another because they should be showing the exact same thing. And then so our complex events here. So these 2 are the complex events. So again, you can see there's multiple bumps in some of the source time functions for this event here, except the one up here and this one here, which is probably due to them having a lot of noise or attenuation in the path for that one. And again, the spectra is deviating from the model a lot, agreeing with the source time functions. And this is one over here, same thing, we're observing multiple bumps, matching the spectra. Yep, I'm almost there. And so here you can basically see that this is the percentage of complex events. So you can see we have a lot of complex events, but then we slowly go down to where we're hitting our resolution limit. So we're observing quite a few, like over a 60 to 80% over magnitude 2.6, which this represents like 25% of the population we get estimates for. So it's significant measurement. And again, we're seeing that artifact of decreasing with our limit. And temporally, we observe that we see a lot of complex events that are bigger, and also they occur right after the large earthquake happens, which is likely because the stress regime is more heterogeneous right after big earthquakes, so more complex events are happening. And then the last one, spatially. So we see them clustering around junctions of faults, which makes sense because this is where stress is heterogeneous, where structure is heterogeneous, so there's barriers and other things preventing ruptures from being circular or simple. So you can see them right here. This is where they're clustering in this kind of bound up here. And they like to cluster right in this area, right above the creeping section of the park field area as well. So, and we observe this in other regions as well. They love to cluster around kind of junctions, parallel faults, things like that, where there's complexity for the stress regime to be heterogeneous. And so I'll end here. But yeah, basically they can tell us a lot, and these 2 methods provide all that information. You want more information, do source time functions, you can get directivity, rupture velocity, and all those things from it. But if you just want a simple, is it complex or not, you can do spectra as well.
Thank you. Time for questions. Yes, Eva.
Colin, thanks for a great talk. So if we think about EGF, the assumption here, we're assuming this smaller earthquake is very simple.
Yes.
So we can use that to consult the propagation path. So what I'm wondering here is that, how much of the source complexity you are seeing from your approach can actually also,
be from the EGF?
By the EGFs?
That is a very good question, and that's an unknown because the EGFs are so small, it's hard to get out their complexity. The thing we usually look at is to see their spectra beforehand and see if we see the bump or like complexity like happen at the high frequency where we're observing the deviation or not. So we do some checks for that, but it's really hard because their deviation usually happens at very high frequencies, which kind of gets the very edge of where we can observe. So
I guess for the nearby events seen by the same
Yeah.
top EGFs, can you see like a simple complex earthquakes just by the same EGF? That would be.
that's another test. Yeah, you could do. You could see if, but these ones we don't really use the same EGFs because they have to be so close to the target event within 200 meters that in order for us to use them or not. So it's a little bit trade-off there.
Or the other way around, sometimes you have multiple EGFs available. Have you tried and confirmed?
Yeah, so we do some like basically. Let's see if I can go back to that slide. So yeah, here, so you can see each of these light red lines is a separate EGF. So you can see all the EGFs here are kind of agreeing that they're observing this deviation. This one here is more scattered, so that one could be a little bit less predictable. This one we're more confident because all the EGFs are kind of showing this deviation.
Are there more questions?
I've got one more. Okay.
Yes.
So here, you talked about the possibility of some kind of path-dependent
Mhm.
variations of attenuation. Do those connect with something you know about the structure of the fault?
It's hard to say with these small like Green's functions because usually we try to get the attenuation exactly the same between events. If they're not the same, we definitely see it. Like things will, especially with the source time function one we're doing in time domain, things will diverge dramatically. We saw like if we did 1 kilometer, which is usually the assumption people do for EGFs, a lot of times they didn't work. We had to get closer, which probably tells us that there's something going on in the fault structure that's attenuating it very strongly. That means they have to be very close to one another for these small events.
Right. We're running late on the coffee break, so why don't we stop here the questions or we continue that over coffee?
Can you hear me? It's fine? Okay. Thanks very much. I would like to thank the organizers for letting me speak at this event. It's really nice. And so my talk is really about one specific phenomenon that's observed experimentally that I'm trying to see how it could play a role in rupture propagation, and the phenomenon is dilatancy. And so this work has been mostly conducted, the experimental side of that work has been mostly conducted by Franz Haben at the time when I was at UCL. So before I move on to the meat of this presentation, I would like us to be on the same page about what is dilatancy. The way I would define dilatancy, at least in this talk, is the increase in pore volume due to shear deformation. And there's different mechanisms by which this can happen. In the bulk, when you deform a compact rock under elevated differential stress and pressures, you have microcracking. This has been established since the 60s. You have these microcracks that are opening at point defects throughout the bulk volume. Within a fault gauge, you may have granular rearrangements that produce changes in pore space geometry and increased dilatancy in some situations. And also we have at larger scale, if you slide on rough faults, you have also the roughness and the geometry can also produce substantial dilatancy on the fault plane. So why do dilatancy could impact the dynamics of ruptures? It's because we have an effective stress principle that in a brittle regime is extremely well established, that tells us that it's an experimental fact, that means that the shear strength of faults and rocks in a brittle regime is very often directly proportional to the difference between the normal stress applied in the fault and the pore feed pressure. So you obviously, if you see that if pore pressure changes, it changes the strength, and it's a first order effect. We're not talking about rate and state effect where we have like very, very tiny variations of these friction coefficients when you change slip rate. This is a very, very large variation directly proportional, that directly goes into play in the shear strength. And of course, the question is, what is the effect of dilatancy on rupture dynamics, and how we relate the pore volume change to the pore pressure change, and then in terms of the strength. So I'm going to briefly spend 2 slides explaining some experimental results, so a subset of a large number of data sets that we we've developed over the years that demonstrate the large impact that dilatancy has on pore fluid pressure and the dynamics in the lab. So we conducted shear failure experiments in initially intact granite. And what we do in this series of experiments is so this is a granite sample from Westerly, Rhode Island. We have a triaxial apparatus that confines the system and imposes some differential load. And we measure stress and slip, but also we developed a technique to measure in situ pore fluid pressure along the fault. So we've developed these sensors that can do this in the lab. And I'm going to show you one example of I would say, typical rupture behavior when you deform westerly granite under elevated pressure conditions. What is the sequence that you see as a function of time before the rupture and just following rupture? So the rupture occurs in two phases, and it's quite systematic. We have a first phase in which here I'm plotting the shear stress, pore pressure, and slip. So the pore pressure is measured on the fault. It's not the one you impose remotely in the system. And so we have an approach to failure where the shear stress starts to decrease a little bit, and that's coincidental with a very large pore pressure drop. So we see we have pore pressure variations of the order of 5 to 10 MPa, and progressive acceleration of slip, and then at the main shock, so the main shock is really the rupture event when you go from intact to broken. We have a very large stress drop, which occurs over like a few seconds, tens of seconds. Very, very large pore pressure drop. We dropped something about 30 megapascals here, locally on the fault, and a step in slip. But then immediately following this, we have a phase where we continue the stress drop in a kind of decelerating way, and we continue slip also in a decelerating way, but at the same time the pore pressure increases. So we have really two distinct phases which are characterized by two opposite evolutions of one pore pressure decrease before or during rupture and increases after. And this is really after slip in a way, right? So it's really occurring on the same fault because there's only one fault in our system here. So what's the way we understand this from a, let's say, experimental point of view? It helps to position ourselves in a more diagram where we plot shear stress as a function of the on-fault effective normal stress. So again, I insist this is the pore pressure measured on the fault. And if you plot the stress trajectory of that experiment, we go from initial strength where we have the peak load, and it drops in two phases. The phase one is when we have intrinsic weakening because we go from intact to broken, so we have like the rock itself is weakening. It's accompanied with dilatancy and a pore pressure drop, which is essentially the fact that the pore volume increases, the system doesn't have time to drain into the pore fluid reservoirs that we have next door, and so the pore pressure drops. So it means the stress trajectory goes this way. If you were to plot a Moore circle, I didn't do this because it's very big, but essentially the Moore circle would go on to the right-hand side of this diagram. And the weakening and the slip is really due to the decrease in friction and/or cohesion during that thing. In the meantime, the pore pressure drops as well, but this effect is not compensated fully by the large frictional or cohesive drop due to the intrinsic change in strength. But then following that, what happens is that the pore pressure has dropped on the fault, but off the fault it hasn't. And so it's recharging. It's like an injection test, except it's just the fault walls are recharging into the fault by a diffusion process. But you still have some residual elastic energy in the system from your loading system. And so it's like conducting an injection test. You slide on the newly formed fault in a decelerating way. And this is an after-slip associated to stress relaxation. So the interesting aspect of this type of experiments is that we can have a sequence of two phases, a weakening dilatant phase followed by a further weakening diffusive phase, which occurs sequentially in time because we have like, in an experiment, everything is more like a point. So you look at what would happen at one point in a material point along the fault. But if you were to upscale that, and that's what I'm going to do next in the model, this type of sequence in time would occur as a sequence in terms of position along the fault, from the crack tip to the tail end of the rupture. And so the idea is that we're going to move from like the zero-dimensional like time sequence into a one-dimensional fault system, where we're going to model these effects and see how they impact the rupture dynamics. So the model is quite simple because I can't really do more complex than this myself. It's an infinite homogeneous elastic medium loaded in mode 3. We have a steadily propagating rupture, so it's a steady state model, semi-infinite fault. And we have two main ingredients. We have an intrinsic slip weakening friction coefficient. Again, you can put different mechanisms behind this, but at phenomenological level, this is a correct description of what happens. And then we have a concurrent porosity increase as a function of slip, which is, again, we can put more complexity there, but again, it's a first order thing. And so these are the two main ingredients, and of course we need to account for fluid diffusion in and out of the fault. And we have two key parameters which characterize this system. We have a pore pressure change due to dilatancy, so we convert that porosity change into a pore pressure change, and a hydraulic diffusion time, which is going to control something regarding the diffusive process at the tail end. And the goal is to compute the slip rate, energy balance, and essentially having a crack tip equation of motion for a crack like this. So I do this two different ways. We have a semi-analytical approach where we can do this almost exactly, and then we have a fully elastodynamic code that can also do this to illustrate what would happen in more realistic circumstances. And so if you solve the slip rate profile and the stress profile as a function of position, I'm going to show you just two different cases here. One case where we have a very, very high diffusivity, essentially the rupture is very, very slow. There's enough time for the pore pressure to equilibrate pretty much at all times during this process. It's a one-end scenario. Imagine if you have like a dry rock or something that doesn't, the pore pressure plays very, very, very little role in the system. So we only have like the effect of the slip weakening curve behavior that we put in the first place. This is the conventional cohesive zone model for ruptures. Maybe it's a slightly different way of looking at it because I plot a log scale for position from the crack tip here. But essentially you have slip weakening, so the strength dropping in the cohesive zone, and we have a peak in slip rate, which is the tail end of which is closely matched by a fracture mechanics prediction. This is a decay of like square root decay of slip rate away from the rupture tip. So that's kind of the baseline case, very conventional. It's just the dry case, if you like. But now if you have a faster rupture or equivalently a lower hydraulic diffusivity, well, the pore pressure is now not equilibrated all the time. You have an undrained behavior at the tip and a drained behavior at the tail end, and it changes quite a bit the behavior. We still see this kind of first peak in slip rate and first strength drop due to the slip weakening behavior that we put. However, the strength drop is limited because you have an undrained pore pressure change, right? So the pore pressure has now decreased. So the strength equilibrates to the undrained value, and then over time, the only way for the pore pressure to change is to diffuse from the off fault. So we have a recharge, a diffusive recharge of the faults from the sides that occurs that forms a very long-tailed weakening behavior far away from the crack tip. And this second stage of weakening coincides with a second slower peak in slip rate. So that's the way you're going from a sequence in time is actually a sequence in space here as a function of position from the tip, because we convert time to space with the rupture speed here in that case. So that's the kind of a detailed simulation, a semi-analytical simulation for this crack tip thing. But how can we understand this? What can we predict from this type of thing? The idea here is that we have two things that happen that are quite separated in space. We have a tip weakening, due to slip weakening, and then we have an equilibration at a lower pore pressure because of dilation, and then over a long time we have this equilibration thing. So we can separate, if you want, two contributions to the stress intensity factor at the tip of this shear crack. One contribution is an undrained contribution due to essentially slip weakening under undrained conditions, and that's what would be a K undrained, if you like. And then a time-dependent one that's due to diffusion far away from this. And so if you put yourself in the context of linear elastic fracture mechanics, this crack is driven by two things. We have an undrained contribution and a drained contribution, time-dependent one. And that's quite an effective way of looking at this problem, because if you now try to make some predictions based on this very, I would say, classical LEFM thing, you can take your complete elastodynamic system. So I'm going to show here the result of one example simulation, where this is a position. Everything is normalized. It doesn't really matter the details here, but it's a snapshot of positions along the crack. The thin line is ahead of the crack, so when there's no slip. The thick line is inside the crack where there is slip. And I'm plotting profiles of shear stress change, and every snapshot is separated equivalently in time. So for information, like if I plot the shear wave speed here, it would plot along a line like this, so very, very fast. And what you see here is that the elastodynamic simulation tells you that there's a very, very weak, slow crack growth rate at over time. That's quite limited. But what's nice is that if you take this an equation of motion, something like K equal Kc, to predict completely analytically the position of the crack tip as a function of time, you get this blue curve. And it's a prediction. There's no fitting parameters involved. It's just a basic prediction from fracture mechanics, which means we can use this concept of separation of scale between the weakening undrained at the tip and the weakening due to diffusion at the tail to then combine that into a very, very simple prediction, which means if you want to predict where the crack is, we don't need to solve the elastodynamic equation. We can do something much, much, much simpler than that. So it's also a good way, I mean, that's the fun part, but maybe the obvious part as well that I should also state is that you see in that case that dilation has massively slowed down this rupture. So we get, after some time, we only get like a very small fraction of the shear wave speed because, for the rupture speed, because everything is limited by dilation. Essentially, the only way for that crack to grow is to have the fluid being pumped in from the side, from the walls. And so what limits the crack growth is purely the diffusion in that case. Again, it's a very specific example of that process, but it tells you that these dynamics, these interactions between the fluid flow and the weakening along the crack can play a massive role in changing the early stages and dynamic stages of rupture. Now, to finish off, there's another way of looking at this problem, which is to say, well, I don't want to know about the separation of scale between crack tip, drain, and drain, whatever. I'm just going to say, imagine I have a classical crack in a sense of linear elastic fracture mechanics. What would be the toughness of that crack if you want to involve all this complexity and essentially lump it into your toughness? Well, actually, you can do that, and actually, it's not a new exercise. There's a Rice paper on this, just like pretty much everything, which tells you that you can really compute an effective stress intensity factor or toughness that will depend on my hydraulic diffusion time scale, and actually, it depends in a way that's captured. But these dashed lines are an analytical approximation to this. Essentially, the toughness scales as the square root of rupture speed, and so this is a very interesting ingredient because then you can put that in your crack tip equation of motion and just solve that. You don't have to solve any detail. If you trust this analysis, that essentially you have a toughness that depends on speed, which is kind of a nice way of simplifying all these complex interactions. So I'm going to finish there with a summary. We have a toughening at increasing rupture speed. We see that dilatancy clearly produces the possibility of slower ruptures than previously anticipated. It's also a potential source of afterslip, as I demonstrated in the experimental part. And it's controlled, I mean, at least in that framework, it's controlled by only a handful of parameters, which are obviously phenomenological in nature, some kind of slip weakening, and some dilatant pore pressure drop, and also some fault width. And I would encourage you to have a look at my postdoc Dongliu's poster. He's going to have a poster, I think, today or tomorrow, or at least this week, exploring some of these ideas in more detail, looking at the interactions between elastic effects, inelastic effects, and so on. And just for a quick reminder, there's a lot of these things that have been published over the years. So please have a look at those papers if you are interested and ever so inclined. Thanks very much.
Thank you. Time for one question while we do the switch. Dimitri.
Very nice talk, really enjoyable. I was just wondering, so I guess what you showed directly experiment-wise applies to the rupture through threshold. Or did I miss it? Was it a cut fault, or it was just rupture?
You start from an intact.
Yeah. So with that in mind, I'm wondering, could you comment to what extent this mechanism is important?
If it's not intact.
If it's not intact.
Well, I think for me, an intact work is a very loose definition. If you have anything that's over-consolidated, if you know your soil mechanics, so if that's your background, you would think of an over-consolidated rock, something that has cohesion, that you would need to re-break if you want to start sliding. And so I think most faults will be like this, especially at depth when you have healing mechanisms over time. It's very unlikely that the fault does not dilate when you start sliding. Again, I think if you don't look at very shallow stuff, it's debatable. But as soon as you have some time-dependent healing or sealing, you will get back to behavior similar to that. We are actually exploring this. But I also think if you have a rough fault, it's very likely as well that the rough fault will, or immature fault if you like, the rough fault will have to open if you want to slide on it. But again, it's not necessarily a universal thing. It's applicable to this consolidated healed fault.
Thank you, Nicolas.
Thank you, Nicolas. Ya. Dale.
Alexis will talk about segmentation of slow and fast earthquakes in scaling mode.
Yeah, actually, I'm not going to talk about that. that was the original plan. Was this the name of the presentation? But yeah, I changed my mind at the last minute. Even though there has been some good theoretical progress in those questions, I realized it was a bit early maybe to present those results. So I'm going to talk about something that is as interesting as the previous topic. And it relates a bit to some ideas that Aitaro was presenting earlier today in relation to fluid-driven slow slip events. And also in other ideas I hear about determining like the maximum size and magnitude of earthquakes, but in this case is the seismic counterpart actually of them. Okay. As a motivation, our motivation from this topic started from injection-induced seismicity. This is a case to motivate a bit the talk. This is an hydraulic fracturing operation in Canada. So what you see here with the red line, is a well in which fluids are injected in a reservoir to create hydraulic fractures. And what the authors came out in this analysis was that these hydraulic fractures intersected a pre-existing fault, pressurized the fault, and induced a seismic slip at the depth in which the lithology is expected to slide stably in terms of friction. And eventually, this seismic rupture that was propagating faster than the diffusion of pore pressure would be stressing rather unstable regions and lithologies and trigger seismicity, and eventually this earthquake of magnitude 4.1. So this is the class of phenomena that we are interested in. And specifically, the scientific question we want to answer here is like, for a given operation, how large is the region where earthquakes are expected to be triggered by injection-induced seismic slip? So essentially what we want to do is to determine, for a given operation, the distance from the well in which you expect to have this kind of a triggering of earthquakes. And this is an important kind of important information for operators and regulators in terms of seismic hazard analysis. There is a second question also that I will try to reply, which is related to understanding how the moment magnitude of this class of events scales. This is, for instance, these are the largest injection-induced slow slip events detected thus far from INSAR slip kinematic inversions. They found these two events that you can see here. They are in the order of a few kilometers length. And essentially, what we like to, these are the largest event detected so far, but there is plenty actually of evidence for more events in the literature. And essentially, what we want to understand is how large is the moment that these seismic slip events can release for a given injection operation. So in short, the presentation will reduce to essentially try to find some understanding of these two important parameters and how they scale during or with which kind of parameters they scale in an injection operation. So to that, the first part of the talk, I'm going to talk about the theoretical scaling relations we derive for this kind of events. Essentially, we build a physical model in which we have a single planar fault in a three-dimensional domain, and we inject fluids in an arbitrary manner. And this fluid diffuses through the fault, pressurizes the fault, and induces this seismic rupture that for the sake of simplicity, I'm idealizing here as a circular rupture in this case. So this is a relatively simple homogeneous model. Stress, material, and friction are all homogeneous, and we consider a slip weakening friction law at the interface. It is convenient to define this factor, so-called lambda, which is essentially the ratio between the rupture radius and the position of the nominal pore pressure front that would be somewhere here. This L of t is this classical diffusion length scale, which is proportional to the square root of time, where alpha is the fault hydraulic diffusivity. So this model, we analyzed it in detail in a recent paper. And I'm not going to explain this because it would take like half an hour alone. But just to show you that basically there are many regimes in which a seismic slip can happen in this model. And this is essentially determined by three-dimensionless numbers that I won't explain either. But the important thing here is that this, in all of this regime, this essentially lambda factor can be essentially anything. So it can be sometimes much smaller than 1. And that means by its own definition, that is a situation in which the pore pressure front is way ahead of the slip front. It can be also of order 1, which is rather the case I'm showing here, in which the two fronts are more or less of the same order. Or it can be much larger than 1, which is a situation as the one I was showing in the motivation in the first slide, in which the slip front is propagating ahead of the pore pressure front. And it's actually this regime of a seismic slip propagation that what we are interested in, because we want to determine an upper bound for these quantities and under generally uncertain conditions in a reservoir in terms of stress and hydraulic properties and etc. This is the regime that provides the larger rupture for a given injection. And because we studied in detail this model already in the past, we know exactly actually where this regime of lambda much bigger than 1 is happening. So we know where to go and look at this and come out with this upper bound. So, but in short, I guess, of course, a seismic slip can come at least like in 2 flavors in general. It could be just the nucleation phase of an ensuing dynamic rupture, or it could be just the result of unconditionally stable slip. So a slip that will never become any dynamic rupture in such a homogeneous model. And it's this in this latter regime that we are focusing in this talk. So for unconditionally stable ruptures, we show that essentially the evolution of this lambda parameter looks generally like this in time. One property is that it's always increasing. So the slip front is always propagating faster relative to the pore pressure front. And eventually, we will reach always a late time asymptotic solution that actually is the one that is naturally providing the upper bound in our model. So in this late time solution, we show that essentially the model can be explained simply by linear elastic fracture mechanics and assuming zero or negligible fracture energy in the model. And this is because the evolution of the rupture radius is essentially determined by the competition between the stress intensity factor due to the injection and the stress intensity factor due to the stress drop within the rupture. So by solving that equation, actually, we come up with this equation for the evolution of the of the rupture radius with time. And it's kind of nice because essentially it evolves with the square root of the accumulated volume of fluid due to the injection. So again, this is for sort of any arbitrary injection. And it is nicely separated in a sense that this is the only parameter of the injection that controls the evolution of the rupture radius in this regime. And this is the one thing that people can control during an operation in the injection protocols. Whereas the other factor here does not depend on time is only related to in situ conditions in the reservoir. So frictional properties, hydraulic properties of the fault, and the stress state of the fault too. So it becomes kind of nicely separated like that. And this is a result obtained and valid during continuous injection. But to come out with the complete upper bound, we need to understand also the depressurization stage, because usually these operations, they have injection, then they stop. But of course, a seismic slip doesn't stop right away after we stop the injection. And what happened is that the rupture transition in this initial stage of continuous injection from a crack-like style of propagation to a pulse-like style of propagation. And we have understood also this problem very well, but essentially the rupture front keeps advancing a little bit after shut-in. Slip keeps accumulating on the fault. And this is quantified in this plot, in which I'm plotting here the final size of the rupture, which is normalized. So basically, when this is 1, we have a rupture that stops immediately after stopping the injection. And this depends on a dimensionless number that I won't have time to explain you in detail. But what you have to, I guess, believe me, is that if we move in this direction, we are approaching this regime in which lambda is much bigger than 1. And this is the one we are interested in. So essentially, the rupture can grow up to perhaps twice the size of the rupture at the moment we stop the injection in this upper bound model. And this is a factor that is taking into account the shut-in stage, but also correcting for the non-circularity of the rupture, because the previous formula I showed before is valid for circular ruptures. So we could do then analytical calculations under that assumption. So in the end, this is the equation for the upper bound. Essentially, it depends on the square root of the volume we inject, this parameter that depends on in situ conditions, and this relatively small factor that corrects by the shut-in stage. So then we compare against observations we compile a global data set for injection-induced seismic slip events. And this looks a little bit like this. So essentially, we managed to come out with an estimate of the seismic rupture runout distance from the injection point, which is what this Rmax is, and the volume injected during each of these events. So this is across very wide scales. These events here are essentially very tiny ruptures, like this size in the lab, a few centimeters. These points here are also ruptures in the lab, but in the order of a meter. All of this population of points here corresponds to decameter-sized ruptures in underground laboratories during injection tests. And all of these points here correspond actually to field cases, either due to geothermal activities or oil and gas recovery. These two are the INSAR points I showed at the very beginning in the presentation, the two largest ones that are in the order of a few kilometers. So then to compare with the observations, essentially we put all what we don't know, because we know this and we know this from the data in here. And this M factor, essentially, we are plotting it here for different values. And these values comes actually from characteristic values of all the quantities that define this analytical result here for the in situ, the effect of the in situ conditions. And what we found is that essentially it is the fault zone storativity, the main important factor that actually may explain the difference between these two values here. And essentially what we get is that these tiny fractures at the lab has way less storativity than the fractures or faults that we find at the reservoir scale level. And that seems to be explaining the sort of scale dependency that we observe on this M factor in the plot. And as a last thing, here I have like 2 more slides only. Is the scaling relation for the moment release of these events. So upon a series of analytical calculations, we find this simple formula in which eventually, the evolution of the moment release again evolves in these nice ways in which the effects of the operation can be separated from the in situ conditions, but this time it evolves with a 3 divided by 2 power law. And the parameters to which this factor depends are similar as the one as before. So we could, So this is valid again during continuous injection. And then all what we do is just to correct with some additional factors that account for the shutting stage. So the depressurization stage, we have still more slip and a seismic moment accumulating with time. And this is a small factor that corrects by the non-circularity of the rupture. And then we compare with the same data set. We were able to estimate this moment release. And basically, this is the same events that I showed in the plot before. And we find exactly the same thing that before. So basically, with the characteristic values we have for all of these events, this N factor here, essentially, it's decreasing at increasing scales because of the larger storativity that the reservoir have in relation to the tiny fractures that we have in the lab. So with this, I finish. I let you with the summary. And yeah, thank you for your attention.
Time for questions. Dimitri?
Wonderful work, Alexis. But I was, so you have this vast range of slow sleep between the lab and nature, etc.
Mm-hmm.
And you have basically this fault zone storativity, which is basically the thickness of the fault zone that enters which determines a particular curve. But I wonder if you because the thickness of the fault zone of what accommodates the fluid is probably linearly, I mean in a very simplistic terms, linearly scales with size of faults. So, and the size of the fault is exercised perhaps by the largest of those slow slip events. So if you could couple the storativity to basically to the side, to the R, to the side
I see.
events, if they assume to exercise the entire fault, which scales with the
Yeah, that seems a very interesting idea and relation. I didn't think about that. And but when you say that it scales linearly with the size of the fold zone, how do you come out with that linear relationship?
It's just from, I guess, the geologist in the room should support me. But I mean, I think it's basically if the geologist mapping.
Okay, it's an observation.
Of entire fold zones, but also perhaps different units within that fold zone. So obviously, it's probably not the entire fold zone that accommodates fluids.
Mm-hmm.
Some patterns, but
Yeah, no, I see. Yeah, no, very interesting. I think maybe we can.
Sáez and Brodsky is one reference.
Uh-huh.
And Faulkner.
One more question.
Yes.
Thank you very much. But I have one question. So your relationship looks very similar to Magar equation. Maybe you're familiar with that. It's also, but it's used shear modulus instead of parameters you employed in your model. So my question is how your newly proposed equation different with Magar equation? Have you tried to plot
Yes.
data with
Yeah.
Magar? Is it any difference?
I have it in the plot. So I guess the first one is a conceptual difference. Like this is based on rupture mechanics, and because of that, the scaling law depends on the stress state, on the frictional parameters, so things that we expect to play a significant role. And in the Magar relation, those things are of course absent. But still, if we just stick to comparison with data and ignore the theoretical considerations, this is Magar. Yeah, I was here. And so basically, it performs similarly to the case of earthquakes, in which it can explain usually most of the data, except by some points that cannot, like Pohan earthquake in the case of true earthquakes. This would be this point, the Pohan. Is the largest slowest event detected thus far from these INSAR inversions in Canada. So I think but to be fair also, Magar only can change the shear modulus. Instead, we have much more degrees of freedom, right, to move the scaling law. So yes, that's to be fair also with the comparison with the data.
looks more like the Gallis.
Yeah, indeed. Looks more like the Gallis and Pablo equation for earthquakes. And not surprising because both are based on rupture mechanics. Yeah.
All right, thank you very much, Alexis. Take some time for Thea, Mathilde, and then Quentin to come and present in a few minutes the content.